Welcome back to The Explainer. If you're the kind of person who loves to cut through the noise and get straight to the heart of how things actually work, well, you are definitely in the right place today. We're going to dive into a profoundly important mathematical concept. We are going to take all that messy, sprawling, real-world data we deal with every day and transform it into an incredibly organized, absolutely powerful toolkit. That's right. Today, we're demystifying matrices.
I want to kick things off with a bang. Take a look at this quote from the mathematician George Cantor. "The essence of mathematics lies in its freedom." Now, you might be scratching your head a bit thinking, freedom in math? But when we really dig into the source text for our explainer today, it clicks. Matrices actually give us the ultimate freedom. They give us the power to handle massive, overwhelming amounts of information completely effortlessly, letting us solve incredibly complex problems with just simple, elegant structures. And hey, if you thought matrices were just, dry algebra reserved for dusty textbooks, think again. The sheer variety of real-world applications is just staggering. Every single time you open an electronic spreadsheet, you're using matrices. The encryption keeping your private data safe online, cryptography relies heavily on matrices. They're used to track traits in genetics, map human behaviors in modern psychology, project sales trends in economics, and literally rotate those cool 3D objects in your favorite video games. Matrices are basically the hidden engine running so much of our modern world.
So here's our roadmap for this explainer. We'll start off with the power of matrices, clearly define what a matrix actually is, cover the different types, look at some mathematical operations, and finally, wrap up by exploring transpose and symmetry.
All right, let's jump straight into Section 1, the power of matrices, and how we organize information.
Think about it. The core problem humanity has always faced is how to organize information efficiently, right? Historically, mathematicians were trying to solve massive systems of linear equations. Writing out all those variables, x, y, z, over and over and over again, it was exhausting. Plus, it was super prone to error. They desperately needed a compact, simple method. The whole concept of the matrix evolved purely out of this need to shift away from messy natural language and complex algebraic sentences and move into neat, compact mathematical grids.
Which brings us nicely to Section 2. What exactly is a matrix? Let's define the grid.
Let's ground this foundation using a super relatable example straight from the text. Imagine you're reading a word problem. Radha has 15 notebooks and 6 pens. Fawzia has 10 notebooks and 2 pens. Simran has 13 notebooks and 5 pens. Just reading that as a paragraph takes time, right? But here, we've visually chunked that exact same text into a really clean table. The first column tells us about the notebooks. The second is all about the pens. The rows tell us exactly who owns what. We've essentially just built a bridge between everyday sentences and a structured grid.
And this next step brilliantly illustrates the true leap into matrix algebra. When we compare the tabular data on the left to the matrix on the right, what's missing? The labels. We completely drop the names, we drop the words notebooks and pens, and what we're left with is a beautifully ordered rectangular array of numbers enclosed in brackets. Because there are 3 rows going down and 2 columns going across, we call this a matrix of order 3 by 2. And honestly, that is all a matrix really is, an ordered rectangular array of numbers or functions.
Moving right along to Section 3, Types of Matrices. Let's quickly look at the shapes our data can take.
We're going to do a rapid-fire vocabulary check here to help you instantly spot these shapes out in the wild. First up is the column matrix. It is exactly what it sounds like. No matter how many rows of data you have going down, if it is strictly confined to just one single vertical column, boom, it's a column matrix. Its mathematical order is always m by 1, where m is simply the number of rows. Naturally, we contrast that right away with the row matrix. It's the exact opposite. You can have as many columns as you want stretching way out to the right, but if all your data is sitting on one single horizontal line, you've got a row matrix. Its order is always 1 by n. Keep the energy up, we're flying through these.
Now, where things get really interesting, and perfectly balanced I might add, is the square matrix. If the number of rows exactly equals the number of columns, say a 2 by 2 or a 3 by 3 grid, you have a square matrix. This m by m structure is incredibly useful and actually serves as the foundation for a whole lot of advanced matrix operations.
And the absolute rock star, the most famous square matrix of them all, is the identity matrix. Notice the really distinct pattern here. Every number running down that main diagonal is a 1, and every single other spot is a 0. It's so clean.
In the world of matrices, the identity matrix acts a whole lot like the number 1 does in regular everyday multiplication. It's a foundational anchor for matrix algebra.
Okay, let's just pause for a second and take a breath. We have our data beautifully organized into these neat arrays. We know exactly the shapes they can take. But, static data isn't really all that helpful, is it? So, what can we actually do with it? Let's pivot our focus from just looking at the structure to getting into the action.
Which brings us to Section 4, Operations on Matrices. It's time to manipulate these grids.
So, how do we actually put these grids to work? Let's start with simple scaling, which in math terms is called scalar multiplication. The text gives us a brilliant, practical business scenario. Imagine a factory owner named Fatima. She has a matrix detailing all her production numbers across a bunch of different categories. Suddenly, demand spikes, and she decides to double her entire factory's production. In matrix algebra, we literally just multiply her original matrix by a scalar of 2. It is incredibly straightforward. Every single element inside that matrix just gets multiplied by 2. The whole grid scales up perfectly proportionally.
Now let's see how this builds into the notoriously tricky concept of matrix multiplication. Actually, scratch that, it's not really tricky once you see the pattern. It's just not as simple as multiplying matching spots. Instead, we always multiply rows by columns. Think of it like this example from our source text. Step 1, you have a matrix of your requirements, so how many of each item you actually need. Step 2, you have a totally separate matrix of the prices per item. Step 3, to find the total money needed, you take a row from your requirements, multiply its elements sequentially by the elements in a column of your prices, and then you just add those products together. It's a deliberate, systematic weaving of rows across columns that perfectly calculates all this complex, layered data into a brand new, highly useful matrix.
And finally, Section 5, Transpose and Symmetry. We are going to flip the grid.
Let's explore some advanced properties by doing something super simple, literally flipping our grid. Finding the transpose of a matrix sounds incredibly intimidating, but visually, it is delightfully simple. To transpose a matrix, which mathematicians note as A prime, you just interchange the rows and the columns. That's it. Whatever was sitting sideways in row 1 stands up straight and becomes column 1. Row 2 becomes column 2. Row 3 becomes column 3. You are literally just tipping the entire data structure on its side. So, the absolutely crucial takeaway here is how this little flip leads us to symmetry. A symmetric matrix is a very special, almost magical kind of square matrix. It's a matrix where, even after you flip it, even after you force all its rows to stand up and become columns, it looks exactly the same. Its transpose is totally identical to the original matrix. A prime equals A. It beautifully shows that certain data sets have a perfect, inherent structural balance baked right into their very numbers.
Man, we have covered a ton of ground today. We went all the way from messy natural language word problems to building structured arrays, scaling them up, weaving them together with multiplication, and finally flipping them to find perfect symmetry. Matrices truly do give us the mathematical freedom to tame massive, overwhelming amounts of data. So I'm going to leave you with this final thought. Take a look around your own world. Look at your budgeting, your weekly schedule, those big projects you're trying to manage. How might you use the logical, structured framework of matrices to organize and manipulate the complexities of your own daily life? Thanks so much for joining me for this explainer. Keep learning, keep organizing, and I'll see you in the next one.